In this lesson, we complete our discussion of hydrogenic systems by introducing one of the most important quantum mechanical properties, spin. In this lecture, we will introduce spin as an intrinsic property of particles, examine its mathematical description, and explore how it helps explain phenomena such as the Stern-Gerlach experiment, spin-orbit interaction, and the Zeeman effect. In an earlier lesson, we learned that any charged particle possessing angular momentum generates a magnetic field. This leads to what we call a magnetic dipole moment, represented by lowercase Greek letter mu. Mathematically, the magnetic dipole moment vector is proportional to the particle's angular momentum L, scaled by its charge and mass. For an electron in a hydrogen atom, the quantization of orbital angular momentum implies that the atom's magnetic dipole moment is also quantized. Both the magnitude of the dipole moment and its z component take on discrete values, determined by the quantum numbers L and m sub L. The formulas for these quantities closely resemble those for orbital angular momentum, except that the Bohr magneton replaces h-bar. Unfortunately, orbital angular momentum alone is not sufficient to fully explain the magnetic properties of atoms. To see why, let's consider the Stern-Gerlach experiment. In this experiment, a beam of silver atoms is passed through a non-uniform magnetic field. From a classical perspective, we would expect the magnetic moments of the atoms to be randomly oriented, producing a continuous distribution on the detector screen. However, that is not what is observed. Instead, the beam splits into two distinct spots. This result clearly indicates that the magnetic dipole moment is quantized. But there's a problem. From what we've learned about orbital angular momentum, the number of possible orientations of a magnetic moment should be 2L plus 1. That is always an odd number, 1, 3, 5, and so on. This applies not only to single electrons, but, as we'll see in future lessons, also to systems with multiple electrons. The allowed orientations should still follow this odd number rule. But the Stern-Gerlach experiment gave us two outcomes for silver atoms, an even number. That directly contradicts what orbital angular momentum alone predicts. So clearly, something is missing in our model. To resolve this discrepancy, physicists proposed a new intrinsic property of particles known as spin angular momentum, usually denoted by uppercase S. It is important to emphasize that spin should not be interpreted literally as a particle spinning like a classical object. Rather, it is a purely quantum mechanical property with no classical analog. You can think of spin as an intrinsic characteristic of particles, much like mass or charge. In 1925, Goudsmit and Uhlenbeck introduced the concept of spin to explain experimental observations such as spectral line splitting. Later, Dirac showed that spin arises naturally within the framework of relativistic quantum mechanics. In non-relativistic quantum mechanics, however, spin is introduced as a postulate. We accept its existence because it is required to explain experimental results. We have to assume that for electrons, spin can take only two possible orientations. This immediately explains the two distinct spots observed in the Stern-Gerlach experiment. The key insight, then, is that orbital angular momentum alone is not sufficient. We must include spin to fully describe the magnetic properties of atoms. Let's look at how spin is treated mathematically in quantum mechanics. We postulate that particles possess spin angular momentum and the operators associated with spin-obey relationships that are analogous to those for orbital angular momentum. If we represent operators for the square of the magnitude and components of spin angular momentum as s squared, s sub x, s sub y, and s sub z, then the individual components of spin do not all commute with one another. For example, the commutator for the s sub x and s sub y component is equal to IH bar times s sub z. Similarly, the commutator for s sub y and s sub z is equal to IH bar times s sub x. And the commutator for s sub z and s sub x is equal to IH bar times s sub y. This means that only one of the components can be precisely determined. Now, the s-squared operator commutes with the operator for any one component. This means that the magnitude and any one of the components can be measured simultaneously with definite values. For example, the commutator of s squared and s sub x is 0. The same is true for commutator of s squared and s sub y, as well as the commutator of s squared and s sub z. These assumed commutation rules mean that, just like for the orbital angular momentum, we cannot simultaneously know all three components of spin with arbitrary precision. Instead, we are limited to simultaneously knowing the square of the magnitude and one of the components, for which we choose s sub z. Just like for orbital angular momentum, we choose a common complete set of eigenfunctions for the s squared and s sub z operators. We do not have defining rules for the spin angular momentum operators, since spin has no classical analog. We also cannot derive an explicit mathematical expression for the eigenfunctions. However, starting from the assumed commutation relations and using a mathematical technique involving what are known as ladder operators, we can show that two quantum numbers, s and m sub s, are needed to define a complete set of common eigenfunctions for the s squared and s sub z operators. Furthermore, the eigenvalues for both s squared and s sub z operators can be derived in terms of quantum numbers s and m sub s. Specifically, if function f is an eigenfunction associated with quantum numbers s and m sub s, then applying the s squared operator on function f gives back f times the eigenvalue s times s plus 1 times h bar squared. It turns out, in order to explain experimental observations, the quantum number s must be an integer or half-integer. Also, applying the s sub z operator on function f yields the eigenvalue m sub s times h bar times f. Just like quantum number m sub l for orbital angular momentum, m sub s is restricted to values from s to negative s in steps of 1. A given type of particle can only have one possible value of quantum number s. For electrons, protons, and neutrons, the only allowed value of quantum number s is 1/2. Nuclei with odd mass numbers also have half-integer values for quantum number s. Examples include carbon-13 also with s equal to 1/2, boron-11 with s equal to 3/2, and oxygen-17 with s equal to 5/2. Particles with half-integer quantum numbers are collectively referred to as fermions. Particles for which quantum number s is an integer are called bosons. Examples include photons with s equal to 1 and nuclei with even mass numbers. The deuterium and nitrogen-14 nuclei also have s equal to 1. The boron-10 nucleus is also a boson with s equal to 3. Note that for nuclei, uppercase I is often used for quantum number s. Let's now apply these general results specifically to the electron. The question we want to answer is, how many eigenfunctions do the s squared and s sub z operators have in common for an electron? And what are the allowed values of the magnitude and z component of the spin angular momentum vector associated with these eigenfunctions? Well, for an electron, the spin quantum number is fixed at s equal to 1/2. This immediately tells us that there are only two possible values for m sub s, plus 1/2 and negative 1/2. As a result, there are two corresponding eigenfunctions, which we denote in Dirac bracket notation as 1/2 1/2 and 1/2 negative 1/2. Now, the square of the magnitude of the spin angular momentum is given by s times s plus 1 times h bar squared. So, the magnitude is the square root of s times s plus 1 times h bar. Substituting 1/2 for s, we find the magnitude to be square root of 3/4 times h bar. Note that this is the magnitude of the spin angular momentum for any electron. The z component of the spin angular momentum is m sub s times h bar. Therefore, there are two possible values of the z component of an electron's spin angular momentum, 1/2 h bar and negative 1/2 h bar. Note that two eigenfunctions are degenerate as far as the s squared operator is concerned, non-degenerate as far as the s sub z operator is concerned. They represent two spin states that have the same magnitude but different z components. Let's now take a look at how electron spin is represented as a vector. For an electron, we know that the spin quantum number s is equal to 1/2. As we have seen earlier, this means that the magnitude of the spin angular momentum is given by the square root of 3/4 times h bar. We have also seen that there are two possible spin states. The first corresponds to m sub s equal to 1/2. This is commonly referred to as spin up or the alpha spin state. In this case, the eigenvalue of the s sub z operator is 1/2 h bar. Let's visualize this vector. Here is the xy plane. Here is the z-axis. Here is an arrow representing the spin vector. The length of the arrow is the magnitude, square root of 3/4 times h bar. Its projection on the z-axis is 1/2 h bar. Note that although we know the magnitude of the spin vector and its z-component, we cannot specify all three components simultaneously. As a result, we can only describe the spin vector as making a fixed angle with the z-axis. The tip of the arrow can be anywhere on this circle that is parallel to the xy plane. We can see from this vector diagram that the cosine of the angle between the positive z-axis and the spin vector is equal to s sub z, which is 1/2 h bar, divided by the magnitude, which is the square root of 3/4 times h bar. It should be easy to show that this angle is approximately 54.7 degrees. We say that the spin angular momentum vector is precessing on a cone of uncertainty about the z-axis at an angle of about 54.7 degrees relative to the positive z-axis. For the other spin state, m sub s is -1/2. This state is commonly referred to as spin down or the beta spin state. In this case, the eigenvalue of the s sub z operator is -1/2 times h bar. Here is what the vector looks like, same magnitude, but with a projection of -1/2 h bar on the z-axis. In this case, we say that the spin angular momentum vector is precessing on a cone of uncertainty about the z-axis at an angle of about 54.7 degrees relative to the negative z-axis. Prior to this lesson, we described the quantum state of an electron by specifying three quantum numbers, n, l, and m or m sub l. To completely specify the state of an electron, we need a fourth quantum number, m sub s. There's actually a fifth quantum number, s, but we do not need to explicitly include it, since for an electron, it is always equal to 1/2. We use the term spin orbital to refer to the complete wave function that takes into account not only the atomic orbital, which describes the probability of finding the electron in space, but also its spin. A spin orbital is equal to an atomic orbital multiplied by a spin eigenfunction. The atomic orbital depends on the spatial coordinates r, theta, and phi. We define the spin coordinate, omega, as the variable upon which the spin eigenfunction depends. To simplify notation, we often use spectroscopic labels for the spatial part, and then indicate the spin state. For example, 2s alpha represents an electron in a 2s orbital with spin up, while 3d z squared beta represents an electron in a 3d z squared orbital with spin down. Another common convention is to use an overbar to represent the beta or spin down state, while no overbar indicates the alpha or spin up state. Let's revisit degeneracy. Degeneracy refers to the number of different ways a system can have the same value of a particular property. Unless otherwise specified, we are referring to energy when talking about degeneracy. Recall that for hydrogenic systems, the energy depends only on the principal quantum number n, as given by -r times z squared over n squared. If we ignore spin for the moment, the degeneracy of the nth shell is n squared. This corresponds to the number of orbitals that share the same value of n. However, taking into account the two possible spin states, the degeneracy of the nth shell becomes 2n squared, reflecting the total number of spin orbitals with the same value of n. However, it is important to note that, so far, we are neglecting something called spin-orbit interaction. Once spin-orbit interaction is taken into account, the degeneracies can be partially lifted, meaning that states that were previously thought are equal in energy actually have slightly different energies. So what is spin-orbit interaction? It's something that we need to add to the potential energy of the electron because of spin. Let's see why. From a perspective of an observer at the electron's location, it's as if the nucleus is moving around it in much the same way that an observer on Earth perceives the sun as moving around the Earth. Since the nucleus is positively charged, it generates a magnetic field that is felt by a charged particle at the electron's location. The strength of the magnetic field is correlated with the electron's orbital angular momentum. At the same time, the electron has its own intrinsic magnetism due to its spin. The interaction of the two magnets introduces an extra potential energy term into the Hamiltonian, which we refer to as spin-orbit interaction. You can think of this as an internal version of the Zeeman effect. One important consequence of spin-orbit interaction is that it can lift the degeneracy of spin orbitals associated with the same subshell, which would otherwise have the same energy. To predict this splitting, we must consider the total angular momentum, which includes both orbital and spin contributions. So now, let's talk about the total angular momentum. For a single electron, the total angular momentum vector, which we denote by J, is the sum of two contributions, the orbital angular momentum L and the spin angular momentum S. Since both L and S are quantized, we expect J to be quantized as well. The allowed magnitude and z components of vector J can be summarized by defining the quantum numbers J and M sub J, analogous to those for L and S. We can calculate the allowed magnitude associated with quantum number J as the square root of J times J plus 1 times h bar, and the allowed z component associated with quantum number M sub J as M sub J times h bar. The question now is, how do we determine the allowed values of the quantum numbers J and M sub J? To answer this, we begin by considering the z component of the total angular momentum. The z component, J sub z, is simply the sum of the z components of L and S. In other words, J sub z equals M sub L plus M sub S, all multiplied by h bar. We define the sum of M sub L and M sub S as M sub J. Now, for any given value of J, the allowed values of M sub J form a set ranging from positive J down to negative J in steps of 1. So what we do is compile a list of allowed M sub J values. We identify the largest M sub J as the largest allowed J. This will then allow us to cross out a set of M sub J values that form a set for this largest allowed J. We repeat the process with the remaining M sub J values. Let's now apply what we just learned to a specific example. Consider an electron in an s orbital. What are the allowed values of the total angular momentum? Let's see. In this case, the orbital quantum number L is equal to 0. This immediately tells us that the only possible value of M sub L is 0. At the same time, the spin quantum number M sub S can take on two values, plus 1/2 and minus 1/2. To find the allowed values of M sub J, we add M sub L and M sub S. Since M sub L is 0, the possible values of M sub J are simply plus 1/2 and minus 1/2. These two values form a single complete set, which corresponds to J equal to 1/2. So in this case, there's only one allowed value for the total angular momentum, J equals 1/2. This result makes physical sense. Because the electron is in an s orbital, it has 0 orbital angular momentum. That means the total angular momentum comes entirely from spin. So we can say that the total angular momentum is just equal to the spin angular momentum and quantum number J equals quantum number S, which is 1/2. Similarly, M sub J is identical to M sub S. Finally, notice that since the orbital angular momentum is 0, there is no spin-orbit interaction in this case. Let's now consider an example involving an electron in a p subshell. For a p orbital, the orbital quantum number L is equal to 1. This means the possible values of M sub L are plus 1, 0, and minus 1. As before, the spin quantum number M sub S can take on the values plus 1/2 and minus 1/2. To determine the possible values of M sub J, we form all possible sums of M sub L and M sub S. Doing this, we obtain 6 values: 3/2, 1/2, 1/2, minus 1/2, minus 1/2, and minus 3/2. Next, we group these values into complete sets. The largest value is 3/2, so one set corresponds to j equals 3/2, with allowed m sub j values of 3/2, 1/2, minus 1/2, and minus 3/2. This accounts for 4 of the 6 values. The remaining values, 1/2 and minus 1/2, form a second set, corresponding to j equals 1/2. So, for a p subshell, the allowed values of the total angular momentum are j equals 3/2 and j equals 1/2. Now let's connect this to degeneracy. If we ignore spin, the p subshell has a degeneracy of 3, corresponding to the 3 possible values of m sub l. When we include spin, but ignore spin-orbit interaction, this doubles to 6, since each orbital can have 2 spin states. However, when spin-orbit interaction is taken into account, the 6 states split into 2 energy levels. The level with j equals 3/2 has a degeneracy of 4, and the level with j equals 1/2 has a degeneracy of 2. Spin-orbit interaction splits the p subshell into 2 levels characterized by different values of the total angular momentum. Now let's look at some experimental evidence for spin-orbit interaction. One important example comes from very high-resolution spectra. A particularly important case is the hydrogen-Balmer line at 656 nanometers. At ordinary resolution, this appears as a single spectral line. However, when examined at very high resolution, we find that it is actually composed of 2 closely spaced lines. This splitting arises from spin-orbit interaction in the 2p subshell. In contrast, there is no spin-orbit interaction in the 3s, since the orbital angular momentum for an s orbital is 0. So what we are seeing here is a direct manifestation of the coupling between orbital motion and electron spin, leading to slightly different energy levels and therefore slightly different photon energies. It is also worth noting that an additional small shift can appear due to the presence of deuterium. This so-called deuterium shift arises not from spin-orbit interaction, but from a difference in reduced mass between hydrogen and deuterium. High-resolution spectroscopy reveals subtle splittings in atomic energy levels, providing strong experimental confirmation of spin-orbit interaction and the quantum mechanical description of angular momentum. Let's revisit the Zeeman effect now that we have introduced electron spin. When the Zeeman effect was first introduced in an earlier lesson, we ignored electron spin and considered only the interaction between an external magnetic field and the electron's orbital angular momentum. In this simplified picture, known as the normal Zeeman effect, the magnetic energy shift depends only on the orbital magnetic quantum number m sub l. Energy levels split into equally spaced components, typically producing a simple triplet pattern in the spectral lines with 1 unshifted line and 2 symmetrically shifted lines. The photon energies for the shifted line's position differ from the original by an amount equal to mu sub b times b, where mu sub b is the Bohr magneton and b is the external magnetic field strength. This model is mathematically straightforward and historically important, but it does not fully agree with what is observed experimentally. When we take electron spin into account, along with spin-orbit coupling, the situation becomes more complicated. The energy shifts are no longer determined by orbital motion alone, but instead depend on the combined effects of orbital and spin angular momentum. As a result, the spectral lines do not split into evenly spaced components. Instead, we observe more complex patterns, with unequal spacing and varying intensities. This behavior is what we refer to as the anomalous Zeeman effect. Despite its name, the anomalous Zeeman effect is actually the more general and accurate description of reality. The so-called normal Zeeman effect is really just a simplified limiting case that arises when spin is neglected. One final comment about the Zeeman effect. At very strong external magnetic fields, the experimentally observed splitting of spectral lines again shows triplets, similar to the normal Zeeman effect. This is called the Paschenbach effect, and it is due to what is referred to as the decoupling of spin and orbital angular momentum. Theory agrees with experiment if we treat the effect of the very strong external magnetic field on spin and orbital angular momentum separately and assume an additional selection rule that the quantum number m sub s must not change during an optical transition. In other words, delta m sub s equals 0 for an allowed transition. Let's conclude with an important example of spin interactions, the hydrogen 21 centimeter line. This phenomenon arises from the interaction between the electron spin and the nuclear spin in a hydrogen atom. In the ground state, the electron is in the 1s orbital, and as we know, its spin could be either up or down. The nucleus, in this case a proton, also has spin, which can likewise be oriented up or down. This gives rise to two possible configurations. If the electron spin and the nuclear spin are aligned or parallel, the system is in a slightly higher energy state. If the spins are opposite or antiparallel, the system is in a slightly lower energy state. The energy difference between these two configurations is very small, but it is measurable. When the electron transitions from the higher energy parallel configuration to the lower energy antiparallel configuration, a photon is emitted. This photon has a wavelength of approximately 21 centimeters. This transition lies in the radio region of the electromagnetic spectrum, and it plays a crucial role in astronomy. It allows us to map the distribution of neutral hydrogen in galaxies. It is also worth noting that interactions involving nuclear spin are the basis for techniques such as nuclear magnetic resonance, or NMR.